All right, let's get into one of the weirdest, most profound mysteries in all of science. It's a story that Albert Einstein himself kicked off, and he gave it this incredible name, spooky action at a distance. So to really get why this is so spooky, we have to start with a rule that's pretty much sacred in physics. You see, in our world, things happen, well, locally. For one domino to knock over the next, it has to physically touch it. Cause and effect need a connection. And there's an absolute cosmic speed limit on how fast any signal, any influence can travel. And that's the speed of light. Nothing goes faster, period. And this idea, this principle of locality, was a huge deal. It was a massive shift from Isaac Newton's way of thinking. You know, in Newton's universe, if the sun just vanished, poof, the Earth would instantly fly out of its orbit. Gravity was just this magical action at a distance. But Einstein knew that couldn't be right. It would break everything. So his universe is local. Gravity is a ripple in space-time that has to travel from the sun to the Earth, and you guessed it, it can't go faster than light. This whole idea is the bedrock of modern physics. It's what makes sure that a cause always comes before its effect. But what if that bedrock isn't as solid as we think? What if there's a crack in it? I mean, what if reality itself has a loophole? Some kind of weird mechanism that seems to work faster than that cosmic speed limit, completely shattering the rules of cause and effect. This really is a detective story. At the center of it is a cosmic mystery. And the prime suspect? The new, bizarre theory of quantum mechanics. It looked like it was committing a crime against the laws of physics. And the person who first sounded the alarm, the chief prosecutor in this whole case, was none other than Albert Einstein. Yeah, this is the charge he leveled way back in 1927. He called what quantum mechanics was suggesting an entirely peculiar mechanism of action at a distance. He was convinced the theory was non-local, that it allowed things to influence each other instantly, no matter how far apart they were. And to him, this wasn't just a little weird, it flew in the face of his own theory of relativity. So, in 1935, he and his colleagues, Podolsky and Rosen, dropped a bombshell, the EPR paper. It laid out this brilliant thought experiment. Picture a particle that decays into two new particles. Because of basic conservation laws, their properties, like their spin, are now linked forever. They are, in a word, entangled. So if you measure one particle and find its spin is, say, up, you instantly know the other one has to be down. But here's the spooky part. Quantum mechanics says neither particle had a definite spin before you measured it. So how did that second particle, even if it's on the other side of the galaxy, instantly know to become down the exact moment you looked at the first one? The EPR paper just laid the whole dilemma bare. It's kind of like having two sealed envelopes. When Alice opens her envelope here on Earth and reads what's inside, somehow Bob's envelope, millions of light years away, instantly knows what it's supposed to say. How is that possible? This puzzle basically backed physics into a corner, and there were only two possible ways out. Two completely different stories about how our universe actually works. So let's break these two stories down. Story number one was championed by Niels Bohr. It says, yeah, the universe is genuinely spooky. Just like you see here, there is a real faster-than-light connection. The fate of the particles isn't decided until the exact moment one of them is measured. Then you've got story number two, Einstein's version. He said, no way. There's nothing spooky going on. It's just like putting a left-handed glove in one box and a right-handed glove in another. Of course, when you open one and see a left glove, you know the other one is a right glove. The information was there from the very beginning, just hidden. It's sensible. It's local. No weirdness. And at the heart of all this, you had these two giants of physics who just saw the world differently. Einstein believed the whole point of physics was to figure out what reality is, to peek behind the curtain. But Bohr, he argued that physics should only be about predicting the results of our measurements. That's it. And most physicists at the time, they sided with Bohr. Einstein got so frustrated he called Bohr's philosophy a tranquilizing religion because he felt like everyone was just ignoring this huge glaring problem. And just like that, for about 30 years, the trail went cold. It was a complete stalemate. Why? Because both stories, Bohr's spooky one and Einstein's sensible one, they predicted the exact same outcomes in the original EPR experiment. So, since there was no experiment you could run to prove one right and the other wrong, the entire physics community just kind of shrugged and dismissed it. They said, that's not physics, that's philosophy. But then, in the 1960s, a new detective showed up, a physicist at CERN named John Bell. He decided to reopen this cold case. He really felt that Einstein had been onto something important, that he was right to be worried. So Bell started thinking, was there some way to change the experiment, a clever trick to force these two stories to give different answers? And he found one. Seriously, Bell's idea was just pure genius.
Instead of just measuring spin as up or down, he proposed that the two experimenters, let's call them Alice and Bob, would each randomly and independently choose to set their detectors at one of 3 different angles. Now, if they happened to pick the same angle, the results would always be opposite, just like in the original experiment. But the real trap, the brilliant question, was this. When they pick different angles, how often will their results disagree?
This is where it gets really interesting. The bizarre math of quantum mechanics, that's Bohr's spooky story, it made a very specific prediction. It said that if you ran this new experiment over and over, the results that Alice and Bob got would disagree exactly 25% of the time. Just remember that number, 25%. But here's the trap Bell laid for reality. He proved mathematically that any sensible local theory, Einstein's glove-in-a-box idea, had to have a disagreement rate of at least 1/3, or 33.3%. So suddenly, this deep philosophical argument wasn't about philosophy anymore. It was about a number. All we had to do was run the experiment and ask the universe, is it 25% or is it more than 33%? So, starting in the 1980s, physicists like Elaine Aspect finally did it. They built the experiment. They put nature itself in the interrogation chair, and the universe gave its answer. The results, which have been confirmed again and again, were completely unambiguous. The needle landed, consistently, right around 25%. Bohr was right. Quantum mechanics was right. And the conclusion from that is, well, it's staggering. It's inescapable. That bedrock principle we started with, the simple, sensible idea that the universe is local, it has to be wrong. Locality is false. The big takeaway here is that Bell's test proved that reality can't be both local and have its outcomes decided in advance. One of those very reasonable ideas has to go out the window. As John Bell himself put it, we just don't have a choice anymore. He said we are obliged to invoke something like actions going faster than light. That spooky action at a distance that Einstein hated so much, it wasn't some mistake in the theory. It's a real, fundamental feature of our universe. Okay, so your first thought might be, awesome. Does this mean we can build a faster-than-light telephone and break relativity? But weirdly, the answer is no. Even though the influence between the particles is instantaneous, you can't actually use it to send a message. Why not? Because the outcome of your measurement is totally random. You can't force your particle to be spin up just to send a 1 to your friend across the galaxy. So it's this kind of uneasy truce. Quantum mechanics violates the spirit of the cosmic speed limit, but not the letter, which luckily saves us from all sorts of paradoxes, like sending messages into the past. But, even with that truce, a lot of physicists are still deeply uncomfortable with this spooky reality. So the mystery hasn't ended, it's just evolved. To try and save locality, some have turned to an idea that might be even weirder, the many worlds interpretation. In this view, there's no spooky signal because every time a measurement is made, the entire universe splits. Both outcomes happen, just in their own separate parallel worlds. So the choice we're facing now is different. Do we live in a single universe that's spooky and non-local, or do we live in a local multiverse that's constantly branching into infinite new worlds? And that brings us right back around to Einstein. It's so easy to just say he lost this debate, but that's not the right way to see it at all. The truth is, it was only because he refused to just shut up and calculate, because he dared to ask these incredibly deep questions about the nature of reality, that we discovered all of this in the first place. We uncovered entanglement and non-locality, two of the most important features of quantum mechanics, because of him. He was absolutely right to be worried, and he asked the perfect question, even if the universe gave him an answer he didn't expect. His powerful skepticism left us with a reality that is far spookier and way more wonderful than anyone could have ever imagined.